Welcome to Module 7 in our series on constrained optimization. If you made it past the last 6, good news, this will be a little bit easier to digest. We're really just looking at an example that deals with this fictitious factory. We're going to be considering a situation where we're trying to maximize the amount of profit that this, or income actually, that this factory generates while adhering to some practical constraints on the maximum amount of manpower or energy that we can use. So let's consider a fictitious factory that generates two products as described by these two quantities that populate our primal decision array. So x1 represents the number of units of product 1 we're generating, and x2 represents the number of units of product 2 that we're generating. And so the objective of this factory, as would be for any business, is to maximize the feasible income. Now, a feasible income is one that can practically be achieved, right? It's infeasible to generate income that requires the use of infinite energy. So if we violate constraints in that way, then obviously it's not a feasible situation. Now we're going to formulate this linear programming problem in the standard form, as we have done previously, or more specifically in the last module. And here we see our primal optimization, or our primal objective function. So we want to maximize this objective function, f of x, with respect to x, and it's defined as the product of CT times x, where this C1 represents the sale price per unit of x1, C2 represents the sale price per unit of product number 2, and so if we multiply C times x, then that generates the amount of income that this factory will generate. Now, there are 4 constraints that we have to adhere to. The first has to do with the number of units we can produce. We can't produce more than x max number of units, so x1 plus x2 must be less than or equal to x max. We have an energy constraint. We cannot consume more energy than E max total. So we're going to see these coefficients E, E1, and E2. They represent the energy required per unit to generate this product. So E1 times X1 plus E2 times X2, that tells us the total amount of energy that we need to produce those numbers of units, and it has to be less than our threshold, than our maximum. We have a constraint on manpower, pretty similar, where the variable m represents the amount of manpower in a given time period required to generate a single unit of x1 or product number 2. And so we take the weighted sum of those, and that must be less than or equal to m max. Now, we also have a constraint on the number of units produced individually, where we're simply just saying that we cannot produce a negative number of units, right? Worst case scenario, we can use all of our energy and manpower to generate one product and create none of the other. So here we have our primal optimization linear programming problem presented in the standard form, and we're adhering to all the normal conditions, or the normal way we present this. So it is a maximization problem. It employs inequality constraints only, and it is subject to this constraint on the primal decision variable that it must be greater than or equal to 0. And I don't think there's any need to explain these expressions again. We've kind of already talked about them. AH, right, they represent the coefficients of x within the inequality constraint. So for example, this is the amount of energy required per unit of product number 1 to create that. M2 represents the amount of manpower required per unit to create product number 2. Okay, so in the last module, I wanted to make a quick clarification on duality and how it applies to linear programming problems. In the last module, I stated that strong duality always applies to linear programming problems. That's kind of true. It doesn't always apply. What I meant was that generally it does for most practical or meaningful problems. So strong duality applies to linear programming problems with the following assumptions. First, the primal problem must be feasible, so it must define at least one feasible state or subset of feasible states. For example, we can't have a case where the inequality constraints dictate that x minus 3 must be less than 0 and minus x plus 3 is less than or equal to 0, right? There's no value of x that satisfies both of those. Second, the dual problem must be feasible, so we can't have any infeasible inequality constraints in the same way. And the primal problem must be bounded. It can't have an optimal value of infinity if we're talking about a maximization problem. So in other words, strong duality applies to linear programming problems that have a meaningful solution. All right, so let's take a look at the dual solution process. The first thing that I did was generated an ideal solution, and you can see the MATLAB code up here. I decided this time to use an exhaustive search. By no means the most eloquent or most efficient method, but I wanted to switch it up a little bit. So this requires us to define a set of discrete points within our feasible space, examine each point, supplying it to the objective function to generate its optimality quantitative value. We quantify that optimality for all the feasible points, and we just choose the one with the maximum benefit. So if we use that MATLAB script, we end up with the following optimal solution. So optimally, we generate 22 units of X1, 44 units of X2, and the total income generated by the factory is 72.6 units. Now let's say that we're not going to solve the primal linear programming problem. Let's assume that we can't do that efficiently, and so we're going to look at a dual problem formulation. Pretty close to the one we described in the last module. So we must define one dual variable, mu, for every constraint. We have 3 constraints, and so we have 3 Lagrange multipliers, or 3 dual variables. Now here, this slide is a pretty close recreation of one of the final slides from the previous module, where we're simply just performing the transform between the primal and the dual representations of this linear programming problem. We don't have to derive it. It's a cookie-cutter, predefined approach. So for the primal problem, we see that the objective function is equal to C transpose times X. Our objective function for the dual formulation is the dual Lagrange function, which, as we defined previously, is BH transpose times mu. All right. On the left-hand side for the primal, we have a constraint that AHX must be less than or equal to BH, B sub H. And on the right-hand side, we have AH transpose times mu must be greater than or equal to C. Note that this is the same as saying that, right? We can change the greater than to a less than. And then all we have to really do is move the appropriate elements from the left-hand side to the right-hand side. Here's C, here's C, here's B sub H, here's B sub H. We take our A sub H, we transpose it, we move it over there, and then we use the dual variables where appropriate, and we have the requirement, the dual feasibility requirement, that mu k is greater than or equal to 0. So there are several ways to solve this dual problem formulation, because what we presented on the previous slide was just the problem formulation, the dual problem formulation. It's not solved yet. One way we could solve it is to apply the KKT conditions, do this by hand. However, we've already demonstrated this by hand process several times, and so for this module, we're just going to employ MATLAB to solve. In today's world, solving by hand is generally impractical. Well, then why did we do it in previous modules? Because it's a good learning tool. And me personally, when I'm trying to learn something new, I always try to do problems by hand as much as possible. So here we have the MATLAB code that I used to solve. Not much to say here. We can quickly explain it. So we define our coefficients of our primal objective function. We define A sub H and B sub H. So those are the parameters that populate our inequality constraint. And then A sub G and B sub G, right? Those are both null because we don't have any equality constraints. And then we can just plug these in to the linear programming function. And you can see that actually I wrote it twice. So in the yellow, I have a comment that shows how this would be applied to the primal formulation, and then below is the dual formulation. So in both cases, we're calling the linear programming function. In the first spot, we need to put the coefficients of the objective function. For the primal, that was array C. For the dual, okay, our objective function is really the dual Lagrangian, and so the coefficients of that were B sub H. Then we have to put in the coefficients of our inequality constraints, which for the primal is A sub H. For the dual, it's negative A sub H transpose. Again, that comes from right here, right, where we restated our dual inequality constraint as a less than or equal to type expression. Then in the third spot, for the primal, we would put the offset or the constants associated with the inequality constraint. That was B sub H. For the dual problem, it would be negative C. And then here, null, 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 because we don't have equality constraints for either one of these. Then I just set the minimum value, and actually there should be only 2. Set the minimum value of X, assuming that it's 0. We set the minimum value for mu, assuming it's 0. Now, one important distinction is that the first formulation, or first line here, is solving for X OPT. This is not solving for X dual OPT, right? We don't know that. It's solving for mu, and you can see that below. It's solving for mu dual OPT. And then I also set maximum, there should only be 2. So I'm telling the linear programming function that X will have a value less than 50, and I'm telling the linear programming function that mu will have a value less than 50. And so it spits out these values, mu1, 0, mu2, 0, mu3, 1. And here is the minimum right, if we minimize with respect to mu the dual Lagrange function, we end up with 72.6, which was equal to f of x OPT. And so we can see that strong duality applies. But moving forward, let's ignore this for a second. Let's assume that we didn't have that ideal solution moving forward. All right, so let's examine the results. If we look at the solution that the primal problem yielded, and we did this via exhaustive search in MATLAB, it yields an optimal value of x, 22 units and 44 units, and it yields an optimal quantitative value, which represents the objective function. Essentially, the maximum income is 72.6 units. The dual problem, was solved using the linear programming function in MATLAB, and it yields these optimal mu values, as well as a minimum value of the dual Lagrange function, which is 72.6. Now note that the dual solution doesn't give us a value for x. We only have an idea of what that is because, we kind of cheated and solved via the exhaustive search in the beginning. And so we can see that strong duality applies because the primal objective function substituted or supplied the optimal x is equal to the dual Lagrange function supplied with the optimal or the dually optimal Lagrange multipliers. All right, so let's talk about the significance of one of the mu's being equal to 1. Each dual variable, we know, is associated with a single inequality constraint. And so if a given mu value is equal to 1, then the corresponding kth inequality constraint is active or binding, and that's the case where we know that it's equal to 0, right? This is not the first time we've seen this. We talked about KKT. We spent a lot of time talking about active, inactive, binding, non-binding constraints. So, and we've already observed that the inequality constraint, a binding inequality constraint, can be converted to an equality type constraint, right? Again, very similar to how we applied KKT. So, for example, right, we saw in the solution yielded by the previous slide that mu3 is equal to 1. The third constraint is the manpower. And so m1, x1, m2, x2 should be equal to the maximum value. All right. So, like I said a second ago, the dual solution doesn't define any x value. And we asked the question, can we generate this x value from the optimal mu value? And the answer is maybe. Okay, in this case we can, because of the number of constraints that are binding as compared to the number of primal state variables, primal decision variables. So we have two observations that we can use here. Okay, the first has to do with strong duality. Okay, the dual problem told us that the minimal value of the dual Lagrange function, or the value of the Lagrange function when we substitute in the optimal mu's, is 72.6. Okay, we know that strong duality applies, not because we cheated, okay, but because of those three constraints, right? The primal problem is feasible, the dual problem is feasible, and it's an unbounded solution. Okay, so we know that these two are equal to one another. So we know that this is equal to this, we know this is equal to this, and so therefore we know that f of x OPT, which is C transpose x OPT, is equal to the minimal dual Lagrange function is equal to 72.6. We don't really need this in the middle, right? We can use this as a constraint. Then the fact that mu3, or the third Lagrange multiplier, equals 1 tells us that our third constraint is binding. m1 x1, m2 x2 equals 72.6. Now note that the fact that these two numerical values match, that's not necessarily something that's always going to be the case. With the strong duality assumption, we may solve the dual problem for x OPT using just some basic linear algebra. Now, this may not always be the case. We're going to see that if we had 3 state variables, we would actually be one constraint short of solving. For this case, specifically. All right, so on the left-hand side, we have our original primal linear programming problem, and we can't solve this just the way it is without doing some sort of maximization, right? But what we can do is convert this, as well as this, we can convert those into constraints. So we don't need this, right? What we'll have is two functions that are in terms of two variables, and yeah, we can go ahead and solve that. And so we use this MATLAB in order to do so, although, one can see that we really could just set this up as a linear algebra problem, right? We really could just say C1, C2, M1, M2 times X1, X2 equals me see what the values would be on the other side. So 72.6, and then whatever the M max value was. This is defined within the MATLAB code. We do have an actual numerical value for that. And then we can invert this and then solve. But over here in the MATLAB, you can see that I used a predefined function in MATLAB. Anyway, to make a long story short, right, we define array C, our matrices, we go through and solve, and we end up with the same value. So what we did was we applied the knowledge we took away from the dual problem solution, okay, and the fact that strong duality applies. We were able to take our original linear programming problem, change some of the, I don't want to say inequalities, but this is a maximization, this is an inequality. We convert those to equalities, and then we can solve. So that's one way where we can take the solution to the dual problem. Again, it's pretty reliant on strong duality applying. That's generally the case. So we can take the dual solution, work backwards using the primal problem statement, and then come up with our x values, which, as we would expect, match those generated all the way in the beginning by the exhaustive search. Okay, so that marks the end of this module. I hope you found this example interesting and meaningful. Like I said, it's a little bit easier than some of the previous modules, not a lot of theory, but it's a good opportunity for us to use some of the tools we've learned over the last couple of modules. And what we saw was that we were able to solve using both the primal linear programming formulation as well as the dual linear programming formulation, and then take the dual solution, which doesn't explicitly give us x, use some observations, and work backwards from the dual solution to yield x. So the final module of this series on constrained optimization is a really interesting one I hope you'll stick around for, and it discusses an economic interpretation of duality, diving more into mu, how it's related to shadow prices. What is a shadow price? What's the practical implication of that? What's the physical meaning of those shadow prices? And for those of you that have an interest in economics, really bridging that link between these theoretical constrained optimization problems and the real types of economic problems that we see in the world.